explain the biasing arrangements, this particular class you understand this particular circuit. And finally you end up with the complete understanding of op-amp design in this analog circuit course. And after that, using analog circuits, what are all the circuits that we can prepare will be taught in this analog IC design course. And the idea course is what is happening right now at this moment. So what are all the research aspects of it? What are all the future prospects in this particular area? The reason for that I will actually explain in a moment. So this is what's happening in the world with other academic institutes. So this is our main focus. So whatever we do, we actually teach fundamentals and we actually have advanced courses. But in each and every course, there is a project component involved. So if you look at it, once the fundamentals are taught properly, depending on the course level, there will be a 20 to 40% weightage on the projects. So these projects will continue all the way. So first it starts as a course project, and the same students will continue that as a mini project, which is like a 2 credit course in itself for 6 months. And then after that, it becomes a BTech project. So finally, when we take the students all through from starting from the fundamentals to the advanced courses, we will train people in such a way that there will be quite a bit of research publications and focus for undergraduate students. I mean, the undergraduate students not only get the feel of research, but they are doing research at IITHyderabad, and this is an evidence for that. So in the last passed out batch, 21 out of 48 students have published in reputed international and conferences and journals. So that's an achievement in itself, given that we have started pretty recently. Now that's all about the teaching part of it. Right now, what is so important here? So in the past decade, what has happened is like in microelectronics, well, as you know, all the equipment are really costly, and we were actually trying to do a catch-up game. So the technology is moving so fast. 1.5 years time, the technology is changing, and we were not able to catch up. So that was happening in the past decade. But fortunately or unfortunately, that has hit a dead end where the leakage constraints, lowering the device dimensions could not go beyond this particular point. So 22 nanometer technology stopped at that particular time, and people have shifted their paradigm towards looking at from single core to multi-core. Dual core, quad core computers have come in. Right now, again the problem is, if you look at how do you actually connect all these multi-cores today, you tend to connect it horizontally, but the interconnect delays between one core to the other core are becoming limitations. So how do I solve this problem? This problem has not been addressed so far. At this particular point of time, we are actually starting with the other competitors in the world. So we are on par with it, and not only that, we have gained a lot of advantage in the recent years. The main advantage is this infrastructure. Today, if you look at the infrastructure available in IITs, it is on par with most of the world-class institutions. So I'll just take a simple example to explain and illustrate what I mean by that. So if I look at microfabrication, if I want to fabricate a MOSFET, all I need to do is to follow these particulars. One, first of all, I'll take a device, I'll take a base substrate, I pattern it. After patterning, I etch it in the regions where of interest, I keep the material, and in the regions non-interest, I remove the material. Again I'll deposit the materials of interest. So it is a continuous loop of pattern, etch and deposit. This is what microfabrication is all about. So you actually have different techniques of deposition, you actually have different techniques of patterning, you actually have different techniques of etching. But everything you can actually combine and make them fall in a particular category, and these are all the steps that are involved in microfabrication of a particular device. And continuing, the example that we can take is like, let's take a simple MOSFET that we wanted to fabricate. So these are the steps involved. Take a silicon wafer, open the windows for source and drain, and then by protecting the other regions, deposit a fluoride dielectric, and then deposit a metal contact on source, drain and gate. So these are all the simple steps that we can talk about, and how we actually make it. So I'll not explain the complete pattern, but I'll take one simple step, and I'll show you that we have the capability to do not only the MOSFET of previous era, but also the MOSFET or the devices of the present era. So if I look at it, let's take a simple step of opening the windows for source and drain by protecting the other windows. So what we need to do is, with you take a silicon wafer, you have a protective layer on top. So how do I get this protective layer? We can either do oxidation or low pressure chemical vapor deposition or plasma enhanced sealing. And this is the instrument that we use for that particular purpose. So we have this even smaller instrument. After that, you actually do a spin coating. You do a photoresist system wherein you expose UV light through this photoresist material, and this pattern gets transferred onto the photoresist. And the equipment required for that particular application is a UV analyzer and UV aligner, and we have this particular equipment, and this has the capability to actually make patterns of the dimensions of the order of 1 micron, and there is a special component involved in that wherein you get the nanometer dimensions as well. There is this nano imprint lithography equipment that we have purchased, which can fabricate the dimensions of nanometer dimensions. After that, if I expose it, and if I want to develop it, we need a wet bench, wherein you have to have ultra pure chemicals and do a wet chemical processing involved. So if we actually look at it, slowly we have shifted to a regime wherein everybody thought that electrical engineer has to deal with electrical subjects, mechanical engineer has to deal with mechanical subjects, and everybody was focused on a particular discipline. This whole area will have come up if that were the case. So right now the explanation is so broadened out that the boundaries between two engineering departments has almost vanished, and the focus is on interdisciplinary research. And this is one of the perfect examples. If you look at it, the wet chemistry is all given by the chemistry people, but we execute it as microelectronic engineers. But without their knowledge or without their support, we cannot do it. And so devices, they cannot use the devices without our support. So that being the case, it's a handshaking between different departments that's happening. So we similar process steps that are involved in this particular process. So already you are trying to convert N region into a P region. So we use a diffusion stack furnace, again the same instrument. So and then after that we remove the protective layer. It becomes we need to use this particular. In essence, what I am trying to get at is, look, if we envisage a device that we want to fabricate, we have all the facilities that are required to get the device into working condition. So we have the capability. Now it comes to how do I look at and how do I envisage, how do I design. So the capability of execution is already there with us. So not only that, if you might have a clear understanding that if you look at centers like Center of Nanoscience and Engineering at IISc and Center of Nanoscience and Engineering at IIT Bombay, they have the state-of-the-art facilities in India right now, and they have got developed in the past few years. And if you look at the equipment, if you compare a list of equipment, the basic equipment that are required for executing the fabrication steps, most of them are actually present at Nano X facility in IITHyderabad. So these are all the state-of-art facilities that we need to have to design and develop any device that is possible. It's not only microelectronics. You can envisage MEMS devices. You can envisage sensor devices. You can envisage IR cameras. Anything that you want to do, the capability is there with us. So just give a little bit equipment. So if you look at it, we have purchased equipment here called the xenon fluoride etching, which has the capability of going to very deep trenches in silicon wafer, and that is only there in IITHyderabad. And we have our own specialties. We engineer our device. We actually are purchasing the equipment based on our capabilities, and in that particular process, we end up being in some areas we are actually superior to the existing institute. I mean, in some sense, not in all the senses, but equipment equipment-wise, the quality-wise, we have the capabilities. So, quick equipment at glance. So, we have all the equipments that are required for doing the analysis. So, let me spend some time on this. So, the essence here is we are at the same starting point as this. Look at any other well-developed IITs or IIScs or even world-class organizations, we are at the same point. And the present and future is interdisciplinary research right now. So, I mean, people have actually hit the roadblock. There is 22 nanometer technology, and people are actually looking at exploiting how do I use this particular technology to different domains. So far the focus was on one particular domain, and it has actually shifted, the paradigm has shifted, and application of the same technology has into different domains has led to a different set of products altogether. A simple example, if you take a cell phone, if you are taking a picture, right, if you are turning your camera, I mean the picture vision also turns, I mean there is a horizontal and vertical tilting as well. So that tilting is caused by a device called a gyroscope. It's a MEMS-based device, microelectronics system-based device, that uses the same fabrication technology as is used for microelectronics industry, but for a different application altogether. So it's about the key is about application of microfabrication technology to various domains. The interesting applications I would like to reduce. The interconnect delay has reduced, and the speed of the device can immediately increase. And so far, the technology does not exist, and we are making a significant progress in this particular 3D IC technology, wherein we are actually proving the capability of creating interconnects between two chips altogether. Okay. So similarly, we are working on IR detectors. There are several sensors and actuators that we are working on, and carbon-based polymers, and all these areas are towards, the focus is not towards research, the focus is towards applied research, wherein we want to give a product out. The emphasis is on the product with the research that we are performing. And we want to, the future initiative is to actually start programs like INUP, which is like India Nano Users Program that happens at IISc and IIT Bombay. If there is enough funding, we would be the computators in that particular domain as well. So we are ready to actually serve the nation. Given the amount of infrastructure that we have, we need some other helping hands to make sure that the system runs altogether. So these are all the impacting areas. So so far what the essence here is, microelectronics is about 3D device design and development. We need to be passionate, we need to have perseverance, and we need to have patience to develop all these devices. Only thing that we need to do for students is to actually inculcate the habit of innovation by teaching the basics properly and asking them to explore different ideas. And the future is interdisciplinary research. We have the product orientation. We are looking at any research product. We look for a collaboration with the industry. So finally, I'll conclude with this. So let us progress. Let we succeed. Let us be pioneers rather than peers. Thank you.